Hi everyone, welcome to my talk about on how to build a typical Spring Cloud architecture application. All the code you will see in this session and the slides are available on my GitHub account. I already sent you in the chat. So what's on the agenda for today? First, I will show you how a microservice application benefits from Spring Cloud and how to build it for the deployment on Tanzu Application Service and Azure Spring Cloud. After that, I will show you what's different for the deployment on Kubernetes. Feel free to ask questions via the Q&A functionality of Zoom. Maybe there are also a few of my colleagues in the session who can already answer some of the questions. With the acquisition of Pivotal, VMware is now the vendor of Spring, and Spring plays a very important role in the Tanzu portfolio. Spring is the most popular Java framework with about 80 million downloads per month. The goal of Spring is to simplify and accelerate application development, and due to its auto-configuration, Spring Boot is the foundation for fast development of production-ready applications. Spring Cloud supports the development of microservices architectures by implementing proven patterns, for example, for resilience, reliability, and coordination. And Spring Cloud Dataflow can be classified in the direction of function as a service and enables the building and execution of stream and batch processing pipelines based on Spring Cloud Stream and Batch. On the slide, we see a typical microservice application for a supply chain. In the center of the slide, we have the three microservices implemented using Spring Boot and initially created on start.spring.io. The product microservice only has one endpoint to fetch the list of products, and products are configurable via configuration properties. With the orders service REST API, clients are able to fetch the current orders that are stored in the MySQL database, and they are also able to create new orders. The product ID for a new order is validated with a list of products that will be fetched from the product service via a synchronous REST call. And after the order is created and stored in the database, information like the shipping address will be sent to the shipping service via asynchronous messaging. And after a configurable amount of time, for example, 10 seconds, a status update for the delivery will be sent back via asynchronous messaging to be consumed by the order microservice. Now let's find out what the challenges of a basic implementation like this are and how Spring Cloud helps you mitigate these. The first challenge is that on modern platforms or in the cloud, the IP addresses of our microservice are not fixed and will change over time. So we need a component where all of our microservice instances register their addresses, and other microservice instances are able to fetch that information based on, for example, a name of the microservice to be able to communicate via, for example, REST. Spring Cloud's registry interface solves this problem using popular service registry implementations such as Consul, Zookeeper, or Eureka, and also provides client-side libraries for the mentioned services registry implementations plus Kubernetes. I will now show you how to connect your microservice to an Eureka registry instance. Okay, here we have the order service, the product service, and the shipping service. What I first want to do is add that Eureka registry interface into our order service here. So first we have to add the dependency. So let's go to the POM files. I'm using Maven here. And what I have to add here is the dependency for that Spring Cloud starter Eureka. After refresh, we should now have the library available. Now we have to go to the application here and add the annotation to enable the discovery client. The next step is to configure, for example, the IP address of that Eureka service. With the Eureka .instance IP address, for example, and additionally to connect to the product microservice REST API, as you can see here in the code. We also need that order product API URL. And because of the service registry, we are now able, instead of using IP, to use the name of that microservice. And in this case, it's SE product minus service slash API slash v1 slash product. As we have now fixed the challenge with the dynamic IP addresses with the service registry, let's have a look at the next challenge. For the REST call from the order service to the product service, the order service is now able to get the addresses of multiple product service instances if there is a need for that due to high pressure. Spring Cloud Load Balancer is a client load balancer that helps to spread requests across multiple service instances, and it's really easy to add it to our microservice. First, we have to add the dependency in the POM XML here. It's the Spring Cloud Starter load balancer. After the Maven refresh here, we are now able to go to the application where I have defined that REST template, and that's the REST template used to request the product list. If I now add the load balance annotation to the REST template, load balancing is enabled for it. We don't have to configure anything, but I want to use the Spring Cloud load balancer instead of the default implementation ribbon that is in maintenance mode. Now that we have added client load balancing for the call from the order microservice to the product microservice instances to spread requests, let's try to improve the overall performance of remote calls via distributed caching. To improve the reliability and performance for our calls from the order service to its relational database via JDBC and the product service via REST, let's add a distributed caching solution, in this case Redis, with a Spring Boot's auto configuration and caching abstraction, and in this case Spring Data Redis. It's very easy to add caching to the order service. Just for your information, part of the VMware Tanzu portfolio is also an in-memory data grid called VMware Tanzu Gemfire that is powered by Apache Geode and can be used for microservice caching use cases. Let's switch to the code where I will show you how to implement the caching. Okay, let's start with adding the required dependencies in the POM XML. So the first dependency we have to add is the Spring Boot Starter Cache. And because we're using Redis as a caching solution, we have to add the Spring Boot Starter Data Redis. The next thing we have to do is, for all the entities we want to cache, implement serializable. So let's start with the product. And the next thing we want to cache from the database is the author. We also have to enable caching in the application. The annotation for that is enable caching. And that we can go to the product service where our REST call fetches the products from the product microservice. We are able to add that cacheable annotation on top of the fetch products method. And we have to define a cache name, in this case it's products. Okay, let's do the same for the order repository. As you can see, it's an interface, and currently we have no method where we are able to add the annotations, and because of that, we have to override them. So the first one we are using in the order service is the find all. So let's override it, and there we are able to add the annotation, cacheable, and yeah, let's call the cache orders. We are also using the find by ID here. So let's do the same with the find by ID. And because it's not a list that will be cached, we have to use another cache name. Let's just call it order. We also have that save method here. We have to evict the cache, save. Yeah, that's it. Now we added caching for our REST call to the product service and the database call. Now let's have a look at the next challenge. In distributed systems like microservices, requests might time out or fail completely. If, for example, the cache of the product list for our order service has expired and a request to the product service to fetch the product list fails, with a so-called circuit breaker, we are able to define a fallback that will be called for all further calls to the product service until a variable amount of time to allow the product service to recover and prevent a network or service failure from cascading to other services. Spring Cloud Circuit Breaker supports 3 popular open source options. I will show you how to integrate Resilience for J in the order service. Okay, first we have to add the dependency. The Spring Cloud Starter Circuit Breaker Resilience for J. We want to add a circuit breaker to the call from the order service to the product service. And for that we need a circuit breaker factory. Okay, and now let's add the circuit breaker to the fetch products here. What we have to do is we have to create a new circuit breaker with the circuit breaker factory create method. We have to define an ID. And then there is a run method, as you can see, with a function for the run part and a function for the fallback. I have that call here. I just want to return. The next function we have to define is the fallback. I just want to add logging here. Yeah, and that's it. So if, for example, the service is not available, then instead of cascading that error, the circuit breaker will return an empty list of products. Okay, next challenge. Apps sometimes store configs, for example, as constants in code. This is a violation of the popular the 12-factor app methodology, which requires strict separation of configuration from code. The reason for that is that configuration can be significantly different across environments, but the code is the same. Spring Cloud Config provides server-side and client-side support for externalized configuration in a distributed system. With a configuration server, you have a central place to manage external properties for applications across all environments. Let's see how to configure our microservice to use a Spring Cloud config service instance. The only thing we have to do to configure our microservices to use a Spring Cloud config server instance is to go to the POM and add the dependency. Spring Cloud starter config in this case, and that's it. With so many APIs in a microservice application, developers need an API gateway that they can control. Spring Cloud Gateway aims to provide a simple and effective way to route to APIs and provides features related to security and resilience to them. Let's have a look how you can deploy and configure a gateway for your microservice application with a Spring Cloud Gateway. Okay, let's create a new project at start.spring.io. Let's call it Gateway. Now we have to add the dependencies. First, let's add the actuators. The next dependency we need is the gateway. Spring Starter Security, Spring Starter Config, and Netflix Eureka Discovery Client. If you click here on Explore, we can see all the files that will be generated. Let's now download it. And we'll copy the contents of the zip file into my project folder. And if we now go back to the IDE, we can see it here. We have to add it to our parent POM. Okay, let's just change the Spring Boot and Spring Cloud version to the ones the other microservices have. The only thing we have to do now is we have to set a name in our applications YAML. In our case, we only want to have all the routes to our different microservices available via the service registry. So that's a feature of Spring Cloud Gateway, and we have to specify the spring.cloud.gateway discovery locator enabled. Yeah, and that's it. With the Spring Cloud Gateway dependencies and these two configurations, we now have an API gateway. Distributed systems like microservices have a need for monitoring like they have for a DevOps culture, rapid application deployment, and rapid provisioning because debugging in distributed applications is complex and time consuming. With a distributed tracing and Spring Cloud Sleuth, you are able to track user requests end-to-end across microservice architectures. Spring Cloud Sleuth supports OpenZipkin compatible systems directly. In our example, we are sending the metrics and traces to VMware Tanzu Observability by Wavefront, our full-stack observability solution from infrastructure to application. Okay, let's add the required dependencies. First, the Spring Cloud starter through. And for Wavefront, we have to add the Wavefront Spring Boot starter. We also have to add the BOM for that to the dependency management. After that, we can go to the application properties and, for example, define the application name that will be used within Wavefront. And by default, the Wavefront Spring Boot Starter creates a freemium account without a registration for you, but you have to configure the credentials of the freemium account for one instance for the others to see the distributed tracing instead of just the metrics. If you have a Wavefront account or you want to specify that of one instance for the others, you can do that by the management metrics export Wavefront URI. And the API token. There's not much room left on the presentation slide for additional components that mitigate additional challenges, but there is one more thing, and this is the reason why I didn't show you the implementation of the shipping microservice yet. I implemented the shipping microservice using Spring Cloud Stream, a framework for building highly scalable event-driven microservice connected with our shared messaging broker to communicate with the order service. And I also implemented the business logic via functions so that it's possible with a Spring Cloud function to run it anywhere with familiar Spring APIs. Let's now have a look at the implementation of the shipping service. First, in dependencies, you can see we have all the libraries we added to the order microservice, like, for example, the Netflix Eureka client or the config client. Additionally, we have that Spring Cloud Stream Binder Rabbit that includes all the required dependencies. Like, for example, Spring Cloud Stream. Now have a look at the implementation. We can see the argument of the function and the result. So in this case, it's the order, and as a result, method will return a status update with a status delivered. You can see here the configurable shipping duration, and the only thing that method is doing is having a timer with the duration of the shipping, and after that timer completes, that status update for the delivery will be sent. To configure all that stuff, we have to have a look at the application YAML here. As you can see, for sure we have the definition of the name. And with the cloud stream bindings, we have to define the exchange here where the order microservice sends that order after a new one is created. And for the out, so the result of the function, we have to define the exchange where the order service is watching for the order update. You can also see that configuration of the shipping duration, the default is 0, but for sure you can change it to 10 seconds. And now we have a complete picture of our typical Spring Cloud architecture application. Some of you may wonder why I didn't use more components of the Netflix OSS stack, which was very popular in the past. The reason is most of the relevant Netflix OS projects like Hystrix or Ribbon are on maintenance mode for several years, and it's the same for the related Spring Cloud projects. We mitigated a lot of challenges with the help of Spring Boot and Spring Cloud, but regarding the deployment, there is, for example, still a high effort to manage the cloud infrastructure for the microservices, and the application lifecycle is difficult to manage. Platforms like Azure Spring Cloud take on the challenges and is jointly built, operated, and supported by both VMware and Microsoft. Azure Spring Cloud abstracts away the complexity of infrastructure management and Spring Cloud middleware management, so you can focus on building your business logic, and Azure is responsible for dynamic scaling, security patches, compliance standards, and high availability. Another example for a platform as a service is our commercial Cloud Foundry offering, VMware Tanzu Application Service, the best runtime for the Spring ecosystem with the flexibility to use a lot of other programming languages and frameworks. On the slide, you can see the steps for the initial deployment on both of the platforms. Because the Azure Spring Cloud instance creation takes some time and the command for the creation of services doesn't run in the background, the deployment on Tanzu Application Service is around 30 minutes faster. Both platforms support the binding of services to the application so that credentials will be automatically injected via environment variables. One drawback of Azure Spring Cloud is that this functionality is limited to a few services like MySQL and Redis, and for example, not yet available for the message broker Azure Service Bus. The full deployment instructions are available in the GitHub repositories mentioned here. Let's have a look at the features Spring Boot provides for Kubernetes. Spring Boot 2.3 added the feature to build OCI-compatible containers for your Spring Boot application using cloud-native build packs. The build packs detect what is needed to compile and run an application based on the application's source code. The application is then compiled by the appropriate build pack, and a container image with the best practice in mind is built with a runtime environment. The biggest benefits are increased security, minimized risk, and increased developer productivity. Graceful shutdown allows a Spring Boot application to stop accepting new requests and finish currently executing requests. Kubernetes gives applications a default 30 seconds grace period, and you can enable that feature via the application property server.shutdown equals graceful, and are also able to configure the timeout period, as you can see here with the spring.lifecycle.timeout per shutdown phase property. Spring Boot 2.3 also added actuators groups for Kubernetes, health and readiness probes. Liveness probes are used by Kubernetes to determine if an application is healthy and restarts if that is not the case. Readiness probes are used by Kubernetes to determine if an application is ready to receive requests and does not send network requests to an application that is not ready. And if you run your application in Kubernetes, the endpoints are enabled by default, and you only have to configure your pods, as you can see in the example. Okay, let's first have a look how to build an OCI compatible container image. As you can see here and on the slide, the command is spring boot build image. And in this case, because we're having a parent POM, we have to define the subproject with a PL argument, and we also specify the container tag. That's also possible via the POM XML of the subproject. So let's start the command. First, the application will be built as a jar. And after that, the builder image will be loaded. So in the builder, there are all the different build packs specified, and base OS image. These new cloud native build packs are really modular compared to the old ones from Cloud Foundry. And the first thing that's happening is a detection phase where the builder detects which of the build packs are relevant for that source code, or in this case archive. And after that, the building will be started. It's already finished. What it's doing is adding different layers into the container. Also, the Spring Boot application was built as a layered chart. And these layers are also in the container image. And with that, if you rebuild your application, and normally, or most of the times, the only thing that changes is your source code and not that other libraries or the rest of the stack of the container image. And if you do a rebuild with a new source code, it can use the cache of the layers that didn't change. And with that, your image does use fewer disk space compared to a container image where you have everything in one layer. That's the tag here. And we can see it here if you run the Docker images. So it's in your local Docker registry. And if you would like to use it in your Kubernetes deployment, you can retag it and push it to a remote registry, or for sure also you can run it locally. Okay, let's now have a look at the graceful shutdown configuration. In your application YAML of each of your services, that's specified here. So it's really just adding those two configurations, and that's it. Regarding the live and readiness probes, if we have a look at the deployments here, that's the default path for the health checks and the default port of Spring Boot. If you change that, for sure you also have to change it here. Another best practice you can see here is to set the CPU and memory requests and limits. The memory requests and memory limits should be the same. And with that, the amount of memory is guaranteed. And regarding the CPU, you should set the CPU request for the warmed up JVM and do not set the CPU limit. Let's have a look at the differences of our typical Spring Cloud architecture application on Kubernetes. As you can see, instead of using a service registry implementation like Eureka, where the Spring Cloud Kubernetes, the discovery client lets you query Kubernetes endpoints via Kubernetes service by name. Another difference is that with the Spring Cloud Kubernetes, it's possible to use Kubernetes config maps and secrets instead of the Spring Cloud config server. A service is typically exposed by the Kubernetes API server as a collection of endpoints that a client can access from a Spring Boot application running as a pod. The discovery client for Kubernetes lets you query these Kubernetes endpoints by name. And the load balancer for Kubernetes provides load balancing based on Kubernetes services or Kubernetes endpoints via the Spring Cloud load balancer. Some of you may wonder why you need service discovery and a client-side load balancer if you have Kubernetes services. The most obvious reason is portability for apps that are already using the discovery client and load balancer functionality on other platforms. Another reason is that in Kubernetes, service discovery is limited. So it works great in the same namespace, and load balancing is pretty rudimentary as well. We're also working on new Spring Cloud components that use the full potential of Kubernetes and provide additional value for developers, like the recently launched Spring Cloud Gateway for Kubernetes. Okay, let's first have a look at the POM here to see the dependency. So the Spring Cloud Starter Kubernetes client load balancer here. Next, if you go to the application, you can see we still have that load balanced and enable discovery client, so nothing has changed here. And if you go to the configuration, we can see that Kubernetes load balancer mode service here, and also for the service discovery, the discovery all namespaces configuration. Spring Cloud Kubernetes config makes config map and secret instances available during application bootstrapping, and is also able to trigger hot preloading of beans or Spring context when a related config map or secret changes. The reload feature is by default disabled, and you can enable it via the configuration property that you can see here. And you can also add the level of reload via that strategy. In order for the restart context functionality to work properly, you must enable and expose the restart actuator endpoint, as you can see here. With Kubernetes, the deployment itself is very easy and fast, but it depends on your Kubernetes expertise and how automated the provisioning of the new clusters or namespaces is, whether the initial deployment will take hours, days, or weeks. My recommendation here is to use the highest abstraction available. For example, we launched our commercial Knative offering Cloud Native Runtimes for VMware Tanzu as public beta a few weeks ago. Knative is a serverless application runtime for Kubernetes where you don't have to care about pods, deployment services, or scaling and how to expose your application to the world. Azure Spring Cloud and Tanzu Application Service both support the binding of services to the application so that credentials will be automatically injected via end variables. Our R&D is currently working on a specification for the same functionality on Kubernetes together with IBM and Red Hat. There's some time left, so let's deploy our application on Kubernetes. I already pushed the container images for my microservice that I built with the cloud native build packs to Docker Hub and created a pull image secret in my cluster. As you can see here. Currently, the application is not yet deployed. And I will now create all the required Kubernetes object in the default namespace. All the Kubernetes definitions are in that Kate's deployment folder, so we can have a look at it. You can see all the deployments, config maps, services that have to be installed for the application. So let's create that. Can see that the pods are in the container creating state, so we have to wait for some seconds. We see some errors that because, for example, the database is not yet there. But what you can see here is that we have the deployments for all of our microservices. We have services for those pods. We also have some configuration maps, for example, the product service configuration. You can see that the product names, for example, are defined, so it's using that config map for the configuration. We can start looking at, for example, the product service. So what I have to do is to forward my port. because it's a local Kubernetes cluster. In this case, I forward the port of the gateway service because all of our requests should go through that gateway. And that gateway, based on the service discovery, then forwards the request to the responsible microservices. Okay, now we can curl the products and the order service. So first, let's have a look at the available orders. As you can see, there are none. Yeah, the next step is to create an order. We're then able to see that there's one available with the status created. And if we wait for the specified 10 seconds, we are able to see that the delivery microservice then responded back that the order is delivered. I hope you enjoyed and learned something in my session. Feel free to try out the demos on GitHub, and I will now spend some time on answering questions if there are any.